Hi everyone, my name is Charlie Xu. I'm product manager for C Studio of AI Robotics product line. Welcome everyone and thanks for attending this sharing session. Before we get started, on behalf of AI Robotics team, I want to send out a special thank you to all Rangers for your support. Now let's get started. Today I walk you through how to be a C Studio Jetson product application engineer. The session will be split into three sections. L1, Awareness and Selection. L2, Integration and Development. L3, Debugging and After Sales. Without further ado, let's dive right into it. First section is L1, Awareness and Selection. In this section, I'll explain why our customer choose reComputer Jetson and how our customers leverage reComputer to solve real-world problems. The first thing we can align on is that AI is transforming the world. It can help us write documents, create PowerPoints, write vehicles, or have conversations. Now, AI's capabilities do not emerge out of thin air. They are derived from analyzing massive volumes of real-world data. The process of distilling patterns from such large datasets is called model training. And applying these distilled patterns to solve new problems is known as modern inference. Both training and inference invariably rely on hardware that provides computing power. This could be a supercomputer on the cloud or a low-power device on the edge. Deciding between cloud and edge deployment is an inevitable and a classic challenge in the practical application process of AI. Cloud computing power is more cost-effective, yet less stable, and highly dependent on network conditions. Edge computing power delivers low latency performance, though its computing capacity is limited. With a growing trend of model lightweighting, advancements in chip performance, and the gradual maturation of the edge platform ecosystem, a growing number of system integrators and industry clients are prioritizing edge as the primary form for AI deployment. Now, obviously, there's a wide variety of edge computing devices available, such as general-purpose CPU platforms, such as Intel, NPU platforms like Raspberry Pi and AI Hat, and obviously the GPU platform as Jetson. Users used to make their selection based on actual usage requirements. Out of these three types, CPU platforms offer the highest versatility but fall short in computation power and deep learning capabilities. NPU platforms boast an excellent cost-performance ratio, yet has a less mature ecosystem. GPU platforms deliver the strongest performance, but come with a higher price tag. Among all these platforms, Jetson's most prominent feature is its unmatched computation power. So let's say customers have chosen the Jetson platform. How should they select the most suitable product from C Studio's Jetson product catalog? So the way to do it is that we can assess this from two perspectives. First is the I/O interface, and the second is device computing power. I/O interface determines whether a device can communicate properly with other devices in the system, such as cameras, sensors, and actuators. Computing power defines how much computation a single device can handle, how many models it can run simultaneously, and how complex the task it can process. For example, if the user is designing a physical AI system, he or she will probably prefer the device to have USB ports so that he can connect to cameras, CAN bus for motor control, RS-485 for IMU, and also the computing power to run the VLA model. So in this case, we will probably recommend reComputer Mini J501 to the customer. C Studio has a pretty comprehensive Jetson product portfolio. You can quickly find the right product for customers once you understand the product naming rules. So for example, here, the name is reComputer Robotics J4012. The reComputer, that means it's a C Studio design and a made Jetson-based edge AI device. Robotics indicates the application scenario of the product, which means this product possesses I/O interfaces suitable for robotics application. J4012 means the product is based on the NVIDIA Jetson Orin NX 16GB module, which directly reflects the device computation power. Now that we've clarified product selection methodology, we'll shift our focus to the capabilities of NVIDIA Jetson itself. So what can Jetson do? The most common use cases that we see are video analytics, on-premise large model deployments, and robotics. These scenarios all share a common requirement: high data throughput. So for example, a video analytics system in an airport that analyzes passenger flow for anomalies and detects potential safety hazards in real time. AI-powered smart waste sorting bins that guide users to dispose the waste into the correct category bin based on the waste they have. Local knowledge base, where sensitive data requires analysis and management via on-site AI, where cloud-based large models are not suitable for such scenarios. And also, like tennis ball collection robots that can identify tennis balls on the court and collect them and place them into designated areas. So now we have covered the overall production select methodology, and that concludes our L1 section. We'll have a 4-question quiz based on the material that we just covered in L1 section. So here are the questions. Here are the answers to the first 2 questions. The next 2 questions. And the answers. Now let's move on to section L2, integration and development. Let's explore how to integrate reComputer Jetson into real-life applications. The example we're going to share here is building a C-stickers defect detection system. First, let's discuss the role of reComputer Jetson in the system. Early defect detection systems typically require human intervention to interrupt and execute tasks. For instance, in industrial scenarios, workers had to manually examine whether products met specifications and remove non-conforming units. In the AI era, however, this entire process can now be automated. In an AI automated workflow, the Jetson acts as a compact on-site brain deployed right next to the production line. It gets input data from cameras and the various sensors, quickly determines whether a product has defects or not, and provides inspection results instantly, thus enabling issues to be detected and resolved on-site at the first opportunity. Then, let's talk about how to integrate the reComputer device into the system. This requires addressing 2 key prerequisites. First, power supply and the communication. In terms of power supply for the device, 3 things need to be kept in mind: a voltage, a power rating, and also power connector specifications. For communication between the reComputer and the peripheral devices, please refer to the C product wiki page. It includes instructions and deployment examples on how to connect Jetson devices to various peripheral devices. 3 critical factors need to be verified to ensure such communication between the device and the sensors. They are interface specifications, communication protocols, and the data formats. Now that the hardware part is done, let's move on to how to implement specific functions. Once the hardware interfaces, power supply, and the communication links are all up and running. The intelligence of the system depends entirely on the design of the software stack and algorithm. On an edge AI platform like Jetson, the goal of software development is not merely to run a single model. Instead, the goal is to build a stable, real-time, and maintainable intelligent system. From a software perspective, a complete Jetson system is typically divided into 4 layers: system layer, middleware layer, AI algorithm layer, and the application layer. Naturally, engineers rarely write software programs for a project from scratch. Instead, they modify existing projects for their specific needs. For example, for computer vision models, we can reference the Ultralytics YOLO project. For large model inference engines, we can directly use the off-the-shelf tool like a Llama. And for robotics projects, we can leverage the robot framework. The demonstration video we'll show later will be based on the Ultralytics YOLO framework. Now let's take a look at an example. Suppose we're looking to develop an industrial defect detection system to identify whether the quality of stickers on the production line is up to standard. Let's imagine there's a factory production line where the goal is to mass produce city stickers at high speed. However, the stickers often suffer from damage and cosmetic defects during production. Our objective is to detect defective stickers and to trigger an alert whenever it happens. The traditional way to address this is to assign a worker to monitor the production line on site. This might be the most straightforward approach, but by no means an optimal one. So now we'll demonstrate how to design a sticker defect detection system based on Jetson. First, we need to set up the hardware. For the sake of simplicity in this demonstration, we'll just use a basic hardware setup. We simply connect Jetson to one USB camera and one HDMI display. Now to the application part. First, let's check if there's any off-the-shelf application level solution. We'll ask AI for recommendations. And obviously we'll return a lot of information with a conclusion that no off-the-shelf solution is currently available. So now we'll need to develop the application on our own. We will need to custom train a model tailored to our requirements. The general workflow is as follows. The first, you need to select an algorithm framework. The second step will be data collection. The third step will be data annotation. The fourth step will be to train the model. The fifth will be deploy the model. Sixth, and is adjust the operation logic accordingly after the deployment. Specifically for model training, you train the YOLO model on a PC, which will take about 30 seconds. After that is model deployment. You will export the model output to reComputer Jetson for inference on the edge. After the deployment, if model works as designed, the application will serve its purpose, which is to detect defect whenever there is one, and then trigger the alarm. You will be able to find a video that will demonstrate the entire process that we just described.
In the defect detection scenario of the factory assembly line, how can AI algorithms be used to replace the traditional manual inspection? We can use GPT to help us search for any existing software solutions that can implement the sticker defect detection system. Well, it seems that there is no ready-made software available that can fulfill our detection function. Okay, since there is no ready-made software available to achieve this, the next step is to have it tell us if there are any existing algorithms that can fulfill the defect detection function we desire. Great, it recommended to us the most commonly used and fastest algorithm, which is YOLO, so let's choose it to give it a try. We ask GPT to provide us with a code script for using the YOLO algorithm to call the camera for detection. Copy it to our code and try it out on a reComputer that has the environment set up. try connecting a camera to the reComputer, here's the script given to us by GPT. Here, we use the stickers with the Seed Studio logo to simulate the stickers produced by the factory assembly line. There are both complete ones and those with crease defects. Try running the code on reComputer to see if it works. Oh no, it seems that he can't recognize our stickers. What should we do then? Don't worry, we can continue to ask for help from GPT. Ask him to come up with a solution for us. Summarizing the response given by GPT. The YOLO algorithm has not seen our logo stickers before. The algorithm doesn't recognize them and cannot identify them. Therefore, we need to train the algorithm to be able to recognize our stickers. There are 4 steps. 1. Collect the sticker images. 2. Label the targets to be detected. 3. Train the algorithm. 4. Deploy the algorithm. Okay, let's try following these 4 steps. Step 1. Connect the USB camera to the computer to collect our sticker images. Here we have collected 10 pictures of stickers. Step 2. Go to the RoboFlow website to perform data annotation. Create a new project. Give your project a name and tag the target we need to test. Select the traditional tool. Upload the images we have collected. Choose Label Myself. Use the bounding box tool. Select the area of the target we want to detect in the picture. Assign different labels to the target and then save it. Mark all the images accordingly. Okay, select to marked pictures as the validation set. Save the pictures that we have marked. We can use our reComputer for model training, so we choose Custom Training. Package and download the marked data to the local PC. Choose the YOLO 11 format. Upload the compressed dataset package to Jetson and extract it. You can see that this is the content of our dataset. Step 3. Train our model on the reComputer. We need to download the pre-trained model weights from the official repository of YOLO 11 and save them locally. The model we downloaded here is YOLO 11 and .pt. Okay, just one command is needed. By specifying the path of our pre-trained model and the data configuration file, the training can start. After the model is trained, we can obtain the model weight file best.pt in the runs, detect, train, weights folder under the current directory. Let's copy it to the root directory of the project. Step 4. use GPT to assist us in deploying the algorithm. Copy and paste the code provided by GPT into the Python script of reComputer, and then run the test. You can see that the camera captured our previous target. Then this system would display a pop-up warning for us.
And now here's the quiz part for section L2. And here are the answers. So by now, you should have a general understanding of how to use the reComputer Jetson and how to integrate Jetson devices into real-world applications. So now we'll move on to section L3. This section will be more hands-on. We'll show you how to troubleshoot common issues encountered when using Jetson. Here, we'll focus on three major types of most frequently seen issues: firmware flashing, debugging, and integrating new drivers. First, let's talk about the origin of the reComputer Jetson. Simply put, it's a product redesigned for diverse application scenarios with reference to the NVIDIA Jetson development kit. Now, unlike the development kit, which is only intended for development and testing, the reComputer Jetson features a rich set of I/O interfaces, supports mass deployment, and it comes with after-sales service and warranty. Additionally, there are minor differences in the system software between the dev kit and the reComputer Jetson. The C Jetpack is specifically for reComputer Jetson and is built on top of NVIDIA Jetpack with the addition of carrier board drivers. So the easy way to remember here is NVIDIA Jetpack plus C reComputer carrier board driver equals the C Jetpack. And all these product introductions and the user guidelines for these devices are available on the C Bazaar website and the wiki pages with links shown at the bottom. And here's the Bazaar page. And here's the wiki link. Next, let's go over how to flash the system. Most user-induced issues can be resolved by reflashing the system. The operating system running on Jetson device is Jetpack, which consists of numerous components. Its core components are the operating system, OS stack, and the AI acceleration stack, AI stack. The system flashing process is also fairly straightforward. First, prepare the system image file. Second, set the device to recovery mode. And third, execute the flashing command. For the detailed process, please refer to the wiki pages of respective products listed here. Key notes to keep in mind for flashing. The first is that an Ubuntu x86 host PC is required. And second, the image files vary across different devices. In addition, users can customize their own systems with the open source files that we provide. Follow the guideline on this wiki page, and the users can quickly generate a new image for their own applications. One critical reminder though, do not run the full system update command on a reComputer Jetson board, as this may cause system malfunctions. Next, let's talk about how to debug Jetson devices. Issues are inevitable during actual usage, such as failure to boot normally, device overheating, or unrecognized devices. As application engineers, it's critical that we quickly identify and categorize the issues and then attempt to resolve them. The first step is to identify and locate the issue, which involves gathering the customer's device usage information. In most cases, customers only report the observed symptoms. and that information is not sufficient for troubleshooting. The most direct and effective information comes from the system logs, such as the device boot logs and operation logs, which can be extracted using commands listed here. For the issue identification step, we need to do three things. The first is to confirm the customer's device model and the system version. The second is obtain the abnormal symptoms and the system operation logs. And third, analyze the customer's issue with the help of AI. If you still have no clear direction after these steps, you can always escalate the issue to C engineers for support. The second step is issue categorization, which enables more efficient handling of customer problems. We typically place issues into these four categories shown on this slide. The first one is usage issues. For example, a customer reported no display output, and we later find out the root cause was that the user failed to connect the display to a power source. Second is quality issues. For example, a customer complained about excessive fan noise on the reComputer device. The root cause was identified as uneven thermal paste application in a specific production batch, and the issue was later resolved through rework. Third is software issues. For example, a customer reported the device unexpectedly booted into a black screen after restart. Reflashing the system temporarily resolved the issue, and the ultimate fix was to update the system firmware to address an unprompted automatic firmware upgrade. Fourth is hardware issues. For example, a customer reported Wi-Fi was not working after inserting a Wi-Fi module, and the root cause turned out to be the module not being compatible with the system. The issue was resolved by replacing the Wi-Fi module with a compatible one. The third step is to leverage AI to come up with a resolution. If the solution does not work, then escalate the issue without hesitation, and then you can use the contact listed here. The last common after-sales question is some customers hope to integrate new peripheral devices into their applications. We have pre-integrated most commonly used drivers into the system firmware. If customers need to connect additional peripherals, they typically would need to compile the required firmware for the peripheral devices on their own. To this end, we have created dedicated tutorials to assist customers with driver file compilation, and the links are listed here. So here concludes our last section, L3. Next will be a 4-question quiz for this section. Here are the first 2 questions. Here are the answers. Next 2 questions. And answers. Now, aside from the above quiz questions, we also have a little hands-on project for those who are interested. You can try to complete this task, and after that, you can send the demonstration video to the email address listed here. So that shall conclude our sharing today. Now to the question section, and thanks for watching.